Perfect. That looks good. Thanks, Chen.
Okay. Yeah, sorry about the issue earlier. So I'll begin. So as I mentioned, I'll be talking about a project I worked on during my internship at AWS on using Dafny for verified code generation. And I'll be beginning with the background, followed by um, a brief demo of the prototype we built, as well as explain some key implementation details, and finally discuss our future work. So beginning with the background, using an LLM to generate code from natural language is clearly a very popular idea, and there are many projects that are pushing the envelope on this. Unfortunately, it is not uncommon that LLMs confidently generate code that is suddenly wrong under close examination. So, for example, here on the left, you can find a prompt that asks an LLM to generate an efficient Python implementation of a sequence that is similar to the classical Fibonacci sequence. It differs from the classical definition in that in the recursive step, one takes the sum of the last three entries instead of the last two entries. On the right, we see LLM synthesized code that seems to correctly address the prompt on the left. However, if you look at it a little bit closer, you'll realize that there's in fact a subtle error that causes the code to return the wrong value when n is greater than 2. We will revisit this example again later in the demo. This year, Dafny has become increasingly popular with research at the intersection of LLM-guided code synthesis and software verification. You could say that Dafny-guided code generation lies somewhere in between traditional program synthesis and proof synthesis for math problems, which, for example, DeepMind's AlphaProof targets. One line of research explores prompt engineering and search-based approaches. Here, we have been particularly interested in a paper that uses few-shot prompting to improve the quality of generated code. Another line of research leverages Dafny to catch incorrect code, or to automatically synthesize specifications. Here, we're particularly interested in the consistency checking described in the Clover paper. Now, let us take a look at our current prototype. Before we watch the demo, let me give you a high-level idea of how we integrate Dafny into the code generation workflow first. The LLM, we start on the left with the natural language input of the user, and then the LLM formalizes the prompt in Dafny and returns to the user a natural language translation of the specification. The user is able to give their feedback from the formalization, and the natural language conversation between the user and the LLM continues in the loop until both sides have agreed on a formal description of the problem. This provides a transparent notion of correctness that we can validate a solution against. In the next step, the LLM then generates an attempt at the solution and a proof of its correctness. The Dafny ecosystem will either accept the candidate solution or reject it, in which case it will allow the LLM to refine it or perhaps start from scratch again. This process continues in a loop until a solution appears, or the number of iterations hits a bound that we chose and it gives up. This step is completely automated. Finally, once the loop has converged, the Dafny ecosystem generates additional unit tests for the solution, and it uses its compilers to translate the solution to the target language. In our case, this will be Python, but this could also be Java or JavaScript or any language backend that is supported by the Dafny compiler. The compiler output then may be further optimized by an LLM, for example, to improve readability. Finally, as seen on the right, the user is presented a specification of the problem, an implementation, and unit tests, all in the target language. The correctness of the solution is implicit as it was present in Dafny and has been preserved by the translation. Let us now watch the demo video. We are running a Python chatbot based on Cloud 3.5 Sonnet that was modified such that it uses Dafny under the hood. During the whole conversation, Dafny will remain fully opaque. My prompts will have a white background, and the AI responses will have a gray background. I start by prompting the chatbot with the same inputs that I used for our FibFib example earlier. After a few seconds, the chatbot will respond with a formalization of the problem. This will be a natural language summary of the underlying Dafny code, which is opaque to the user. The slight delay comes from a loop in the background that ensures we only return code that is runtime safe and verifies. Observe that the summary mentions 4 base cases, but in our original prompts, we only had 3. This is because there had been a typo in my original prompts that caused the definition to not be well defined. And the LLM has attempted to fix it here by providing the missing base case. So before continuing with the implementation, I corrected the typo, saying that the last term should be n-3 instead of n-4. The LLM comes back with a new specification of the problem, which looks correct, so we accept it and proceed with the code generation. The next step involves generating an intermediate Dafny program from the specification, but this is hidden from the user. We only see the final result after it has been translated to Python. As you can see here, the final Python program contains an imperative method fibfib, a recursive function fibfibfunc, and a main method with the user-provided test cases. Note that it also includes the additional test cases that were generated by Dafny in the main method. Alright, and that's it for the demo. Let's briefly compare the 2 solutions we have encountered so far. On the left, you see the directly generated Python code from the start of the presentation. It was directly generated by an LLM without going through Dafny. On the right, you see Python code produced by our prototype, which uses Dafny as an intermediate language. The output consists of an imperative implementation, a functional specification, tests that were provided by the user in their prompts, and additional tests generated by our tool. The program is runtime safe, and its correctness is implicit through a proof in Dafny that we generated. The 2 solutions are almost identical, but note that there is a difference in that the program on the left incorrectly returns fib value 0, which would correspond to returning incorrectly A on the right. We've only seen one example so far. Let us now look at some of the broader testing that we have conducted. We've evaluated parts of our pipeline on HumanEval, which is a state-of-the-art benchmark for Python code generation. In the evaluation, we skipped the first loop of the chatbot implementation that allows a user to iterate in natural language towards a specification. Overall, the results are promising. On a set of 164 tasks, the prototype converged to a candidate solution in 144 of the test cases. Hence, this allows it to pass up to 88% of the tests. This is comparable to direct Python code generation, which passed the test in 86% of the cases. These results are surprisingly good to us because there's almost no training data available for Dafny. So for example, on GitHub, there are over 15 million repositories that contain Python code, but only a few hundred repositories with Dafny code. It is also worth noting that after we moved our experiments from Claude 3.0 Sonnet to the newer model Claude 3.5 Sonnet, we saw a dramatic increase in the syntactic correctness of the Dafny code generated. This had previously accounted for a large class of errors. There are still plenty of opportunities to improve these results further, for example, by synthesizing Dafny code for training and fine-tuning. Now that we have seen the results, let me talk about some of the key implementation details. First, prompt engineering. We use a system prompt to provide the LLM with high-level rules that help with code generation by addressing different error classes. First, we stated the LLM's role. In blue, we then specified the LLM's task. Given a prompt that contains a docstring and pseudo Python code, generate from it an equivalent Dafny program. In purple, we specify a format and constraints for the output, so we can extract the generated code and test them automatically. In orange, I explicitly add instructions related to Dafny syntax. For example, I instructed to generate a Dafny method instead of a function, which helps with the LLM mixing up the two due to the older Dafny syntax. I also hinted to use the option data type to handle Python functions that could return none. Finally, I tell it how it should translate test cases into Dafny code that can be checked at runtime. Moreover, we also use few-shot prompting. That is, we provide generic input and output examples to guide the LLM towards returning a Dafny program that has the right structure for further processing. On the left, you see the type of input that the HumanEval benchmarks provide the tool with. It consists of a function signature, a docstring, and a few test cases, all in pseudo-Python style. On the right, you see the type of Dafny skeleton we want the LLM to translate the inputs into before we use it to fill in the part that is currently axiomatized. Notice how the docstring and the function name are preserved and the test cases are translated into expect statements. Given the skeleton you saw on the previous slide, we then use feedback from the Dafny verifier and compiler to iteratively converge towards a provably correct implementation. Initially, the example here, which is a bit more complicated than the initial Fitbit one we looked at, fails the runtime checks since the method is not implemented yet, but verifies successfully. The LLM then proceeds with the first attempt and definitely returns some verification errors. Taking that into account, the LLM then adds an assert statement, which ends up resolving the first error. However, the second error is a bit harder to resolve, and even with the feedback, the LLM does not get it right on the next attempt. Or even the following attempts, although it does end up simplifying the code a little. Eventually, however, it figures out the right assertions to write, and Dafny is able to verify and compile the code successfully. After we have generated this Dafny implementation that correctly implements a specification, we must still post-process it to eventually get the target language implementation. To achieve that, we first use Dafny's native test generation capabilities to synthesize test cases in addition to the ones that were already provided by the user in the prompt. Then we run the Dafny compiler on the generated Dafny code and test cases. Doing so, we're able to obtain their respective Python versions. With that, let me wrap up this talk with some of our ideas for the future. An issue that we struggle with is that the code produced by Dafny's compiler tends to not be entirely idiomatic and requires a Dafny runtime library. One possible solution to this is to use a different, more idiomatic compiler. However, such compilers are not available for all the language backends yet. Another possible solution one can imagine is that we can perhaps post-process the code, and doing so it could improve the readability as well as we can do so using heuristics or even another LLM. Of course, we'll still want to keep our correctness guarantees, so if we were to proceed with this approach, we'd also have to check for semantic equivalence. Finally, another consequence of depending on the Dafny runtime is that the generated code is not always interoperable with native code. So for example, on the left, we have a simple Python code sample returning a list with mixed types. So to model this in Dafny, we'll have to use a custom data type as seen on the right. So while this will compile to working Python code, it cannot be directly compared to the generated Python classes cannot be directly compared to native Python types at the moment. And with that, I have come to the end of my talk. Thanks for joining, and I'm happy to take any questions.
Let's see if there are questions. All right, let's thank you, Chen, again.